All right, so we are going to look at the medicinal chemistry practical, and this will be the second practical. Now, the question says, list 3 ways you could dry synthesized products in the laboratory. Now, one of the ways you can actually dry synthesized products, so I'm answering question 1. One of the ways you can dry synthesized product is of air drying it. You can actually use air to dry them. Air drying, say you should just list, so you can list. Then you can also dry them in the oven. So you have oven drying. Then you can also dry them in a desiccant using drying agent. Are you getting it now? So you can say desiccant, drying in desiccant using what? Drying agent. All right, drying agent. Example of those drying agents is quicklime. We have one like calcium oxide. All right, those are good examples of drying agents. And then you have IV. I think they say just 3, I guess. Yeah, let's just add one more. Lyophilization or freeze drying. You can freeze dry the product. Is that okay? Freeze drying, which is also called lyophilization, is one of the methods of drying products in the laboratory or synthesized product. Now the next question says complete the following reactions involving the synthesis of acetylsalicylic acid, which is also called aspirin. Now aspirin, equation of reaction, so we have number 2. The equation of reaction usually involve salicylic acid, which is something like this. You can say is orthohydroxybenzoic acid. That is salicylic acid. All right, orthohydroxybenzoic acid. That is what we have here as what? Salicylic acid. That is the name. So you can come plus. Now they put a comma here. You have to fill in that in there. Now what will you react with orthohydroxybenzoic acid, which is salicylic acid, to give us aspirin, which is acetylsalicylic acid? You are going to react acetic acid anhydride, or you can say acetic anhydride. So this is going to be something like this. This is how acetic anhydride is. They are the acid anhydride. See that you call it acetic anhydride, or you can call it the acetic acid anhydride. Now this is going to give us a product. Now what product do you think this is going to give to us? A little bit too tiny. Now what product do you think this is going to give to us? This is going to give us a situation where this group here, from here, this hydrogen, all right, is actually substituted with the acetyl group, which is from here like this. Is that okay? To be substituted with this group from here like this. So what are you going to have? You remove this hydrogen, put from here into this equation. It's going to give us aspirin. The only thing they actually want you to add is just this stuff here. I'm just showing you in case they say write the equation of reaction, full equation of reaction, so that you know what to do. So we have O. Is that okay? Then you have C, which is this C. Then you have O, and then you have what? CH3, which is this CH3. So we started with remove this H, then we put this C first, then O, CH3, and then we have COOH. This is the structure of aspirin, which is acetylsalicylic acid. Plus, now recall that when you broke this part is still remaining, right? Which is CH3COO. Plus this hydrogen removed from here is now going to form CH3COOH. So these are the various product and the equation of reaction. So this first one you have here is salicylic acid plus acetic anhydride, or you can call it ethanoic acid anhydride. That means two acetic acid that has lost water. And then this is acetyl salicylic acid. Then the last one here is acetic acid, or you can say ethanoic acid. So that you use acetic acid, or you can call it ethanoic acid. Is that okay? Now, so that is the question number 2. Question number 3. What is the role of H2SO4 in the reaction? That's question number 3. So we come here, answer number 3. What do you think is the role of H2SO4? The role of H2SO4 is that H2SO4 is a catalyst. H2SO4 is a catalyst. Now the next thing is the synthesis of benzoin from benzaldehyde is an example of a carbon-carbon formation. Provide a suitable catalyst for this reaction. Now we are going to do this one in the next question, in the next practical, because I'm taking it practical by practical, so that we should know what we will be expecting in each of the practicals and the questions that we may likely encounter. However, since we already have it here, let me just answer it. The synthesis of benzoin from benzaldehyde is an example of carbon-carbon bond formation. Provide a suitable catalyst for this kind of reaction. Now, this reaction usually involves the use of the nitride. Alright? It usually involves the use of nitrides to catalyze this reaction. The reason is because the nitride act as what? A nucleophile, making the benzaldehyde to be more what? Acidic. Is that okay? So you use nitride. An example of that nitride that is actually used is sodium nitride. So you may be asked, what is the role of the nitride? The nitride is a catalyst. It makes the benzaldehyde to be more what? Acidic, because it's a nucleophile also. Is that okay? If you read your this, you say the nitride group, which is highly specific as a catalyst for this reaction, act as a nucleophile and hence increases the acidity of the benzaldehyde proton. Now, in the next lecture, we are going to look at the mechanism of reaction, because you may be asked to actually show us the mechanism of reactions, because there are some mechanism that we are taught in class. All right. So you are going to know what I mean by the acid being the protons being acidic by virtue of the nitride group there. So they usually use nitride. An example is sodium nitride. Now, the next question here is calculate the percentage purity of 2.5 grams of salicylic acid. Okay, calculate the percentage purity of acetyl. The question, I just frame up this question in case we meet something like this, right? Calculate the percentage purity of aspirin if 2.5 grams of salicylic acid was used and the actual yield was 3.0 gram. So let's see the reaction again. This is the reaction between salicylic acid and what? Acetyl salicylic acid. Now, actual yield, or let's say mass. First of all, let me get the structure, the formula of molecular formula of salicylic acid. It has 1, 2, 3, 4, 5, 6. That's 6 carbons plus this one making it 7. So that would be C7. How many hydrogen do you think it has? Each of these places here, they are hydrogen. So you have 1, 2, 3, 4. 4 hydrogen plus this one here making it 5. Plus this one here making it 6. So you have H6. Then how many carbons do you think it has? we already count the carbon. How many oxygen? 3 oxygen, so O3. So you have it as C7H6O3. Now, how about acetylsalicylic acid? How many carbons? Totally, in the benzene ring, you have 6 carbons, plus this one 7, plus this one 8, plus this one 9. So this will be C9H. How many hydrogens are here? Each of these one is one hydrogen. They have one hydrogen each. So you are going to have 1, 2, 3, 4. Plus 3 here, making it 7. Plus 1 here, making it 8. So that will be C9H8. How many oxygen? 1, 2, 3, 4. O4. Which is acetylsalicylic acid. So this is salicylic acid. This is acetylsalicylic acid. So you can come here and say, by virtue of this, 1 mole of C7H6O3 will give us, from the balanced equation, 1 mole of C9H8O4. What do we mean by that? If you look at this, the molar ratio here is 1:1, or the mole ratio. Is that okay? That is why I wrote this as 1 mole of this is equal to 1 mole of this. So what is the molecular mass? All right. What is the molecular mass of C7H6O3? Now the molecular mass is C7 and the rest. C7 means 12 times 7. Is that okay? 12 times 7. So we have 12 times 7 plus 1 times 6 plus oxygen is 16. So we have 16 times 3. All right, let's press calculator. What do you think that is going to give to us? Let's press our calculator. So this will be 12 times 7 plus 1 times 6 is still sitting at 6 plus 16 times 3. That is 138. Alright, 16 times 3 is 48, which is 138 gram per mole. So this is 138 gram per mole. What this means is that 1 mole of salicylic acid contains 138 gram. How about molecular mass of aspirin? So we have molecular mass of aspirin. All right. What do you think is the molecular mass of aspirin? It will now be 12 times 9 plus 1 times 8 plus oxygen is 16 times 4. If you calculate this, it's going to give us 12 times 9 plus 1 times 8 plus 16 times 4. That is 180 gram. All right. So this will give us 180 gram per mole. It's a very easy something. So if 1 mole of salicylic acid is equal to 1 mole of this, so you now come here and say 1 mole of salicylic acid equals to how many gram? You are now going to say 138 gram of C7H6O3 give us 180 gram of what? C9H8O4. Therefore, now what was the mass of salicylic acid given in the question? I think 2.5. It was given in the question. Look at it. 2.5 gram of salicylic acid reacted. So you are now going to say if 138 gram of this gives this, therefore 2.5 gram of this will be equals to X. Is that okay? Of course, this can cancel this. so that we are going to have cross multiply. This multiplied by this is going to give us 138 times x is equals to 2.5 times 180 x times 180 gram of C9H8O4. Is that okay? Now, at the end of the day, what do you think we are going to have? Divide both sides by 138. Divide both sides by 138. So that this will cancel this, and your x will be equal to, now 2.5 times 180 divided by 138. That will give us 3.26 gram of C9H8O4. This here represents the theoretical yield of aspirin. That is what we are supposed to get from 2.5 gram of salicylic acid. So theoretical yield of aspirin is equals to 3.26 gram of C9H8O4. But now the actual yield, I gave it in the question you'll be given. If the actual yield is 3.0, so actual yield we got was 3.0, so we have actual yield is equals to 3.0 gram of this. And then the next question is the percentage purity. What do you think will be the percentage purity? Now, when we talk about percentage purity, we are talking about actual yield all divided by theoretical yield times 100%. Now, in this case, our actual yield is what? 3.0. Theoretical yield is what? 3.26 times 100%. Now, when this divide is multiplied by 100, what are we expected to have? To be 3.0 divided by 3.26 times 100%, which is 92.02% weight by weight. So this is the percentage yield, or percentage purity rather. So in any case the question comes, you should know what to actually do based on this understanding. Now, I have one more question here, which says, these are questions that I actually just felt may come out under this. What instrument can be used for rapid filtration of the product? Now, for rapid filtration of the product, Mr. Raji was using the suction pump. Alright, suction pump for rapid filtration of the product. Now, another thing that you may be asked is, how can you characterize aspirin? When we talk about the characterization of aspirin, what we're actually talking about is things you should do to identify that this is aspirin. One of those things is the melting point analysis, right? Melting point analysis. Then, of course, those other ones I listed: UV spec. Then we talk about NMRO, carbon and proton. Carbon NMRO and proton NMRO. then the mass spec to tell us the mass. All right, and then the I arrow to tell us the various functional group that are present there. Now, you may be asked physicochemical parameters. When we talk about the physicochemical parameters, we are talking about parameters such as solubility, density, melting point, boiling point, refractive index. Alright, all these ones are some physicochemical parameters. And then lastly, you may be asked the pharmaceutical application. What are the pharmaceutical application of aspirin? It's very easy now. Aspirin is an analgesic. That is all. Right? Aspirin is an analgesic. The one that we know is that aspirin is an analgesic. It has also antipyretic property. Right? Fever, prevent fever, and also antithrombotic because it prevents platelet aggregation. Is that okay? Or you can say antithrombosis, prevent platelet aggregation. So that is every information you need to get for this particular practical. We'll see in the next one.